Oh, op amps, where would we be without you? It is not an exaggeration to say that op amps are found in almost every arena of electronic design. So, if you're going to need an op amp for your next design, you're probably going to need to amplify a weak signal for something. But how do you choose the right op amp for that application you're working on? Well, there is actually a list of design concerns you should consider. First, you're going to need to understand the basic role of the op amp in your circuit. You're going to need to identify the key electrical parameters you need. And then, well, phew, there's more. We should just get started. Hi, I'm Amelia Dalton, host of Chalk Talk. In this episode of Chalk Talk, Christopher John Gozon, or Goz as he prefers to be called, from Analog Devices and I explore the what, where, and how of operational amplifiers. We also investigate the roles that supply voltage, voltage offset, and input bias and input offset current play in op amps, and how you can take advantage of Analog Devices op amp innovation for your next design. And before we get started, don't forget to click that link. There you can find even more information about this topic from Analog Devices. Hi, Guz. Thank you so much for joining me.
Happy to be here.
Excellent. Okay, so we're talking about picking the perfect op amp today. So, Gauze, op amps are found in a lot of different designs, right?
Yeah, so you might not realize it, but operational amplifiers or op amps are everywhere. They're tiny chips that take weak voltage signals and amplify them, making them usable for all kinds of devices. It sounds simple, but they have a huge impact. Think about your smartphone. When you speak into the mic, the signal is way too small for the phone to understand. So op amps come and boost it up, making sure your voice is clear. Same thing with our headphones. Op amps ensure that audio is crisp and balanced. Hop in your car and you'll find op amps all over the place. Your fuel sensor, the brake pressure, the temperature gauge, they all rely on op amps to amplify and clean up their signals, making sure your dashboard readings are accurate and safe. At home, op amps are working behind the scenes too. Your thermostat uses them to read temperature sensors and adjust the heating. That coffee maker you love, the temperature probe inside it depends on op amps to keep your brew just right. Even your smart oven uses op amps to control heat based on sensor feedback. In the medical world, op amps are critical. They amplify signals from heart monitors, ECG machines, and blood pressure monitors, ensuring accuracy in life saving equipment. In industrial setting, they condition data from pressure, flow, and temperature sensors to keep systems running smoothly and safely. So why are they everywhere? Simple, they're small, affordable, and incredibly versatile. They're just like the Swiss Army knife of electronics. Whether you need to amplify, filter, or compare signals, they get the job done.
I love that. Now, Gauze, before we go any further, walk me through the details of an op amp.
Yeah, sure. In order to simplify circuit analysis and design, an ideal operational amplifier is used. It has infinite open loop gain, meaning it can amplify even the smallest voltage difference between its inputs to drive the output to a high or low voltage as needed. It also has infinite input impedance, so it draws no current from the input source, which prevents loading and signal distortion. Its zero output impedance ensures that the output can deliver any required current without voltage drop, maintaining a stable output regardless of load. Additionally, an ideal op amp has infinite bandwidth, allowing it to amplify signals of any frequency without attenuation, and an infinite slew rate, meaning its output can change instantly in response to a changing input. Other ideal traits include zero input offset voltage, so if both inputs are equal, the output is exactly zero. An infinite common mode rejection ratio, or CMRR, allowing the op amp to completely reject noise or interference that appears equally on both inputs. While no real op amp meets these conditions perfectly, these ideal assumptions provide a reliable foundation for analyzing and designing circuits, especially when combined with negative feedback. But there's no such thing as an ideal op amp. Real op amps always come with trade offs. That's why picking an op amp is all about choosing the right one for your specific job. not the best one on paper.
That makes sense. Now, what should my audience keep in mind when choosing an amplifier?
Selecting the right operational amplifier begins with a clear understanding of op-amp's role in your circuit. Once you've defined its function, the next step is to identify the key electrical parameters required for your application, such as input offset voltage, gain bandwidth, input or output impedance, supply voltage range, and power consumption. With those specs in mind, it's important to match the amplifier's performance to the type of application. For example, precision op amps for instrumentation, high speed amps for RF or video, or low power devices for battery operated systems. From there, it's helpful to understand the various op amp families as different categories offer optimized characteristics like rail to rail operation, low noise, or micro power consumption. However, every op amp involves design trade offs. Improving one parameter may worsen another. Finally, before making a purchase decision, practical steps like checking datasheets, reviewing application notes, running simulations, and verifying that the part is available and within your budget. By following this structured process, you can confidently choose the op amp that best fits both your technical needs and your project constraints.
Excellent. Now, Gaz, can you also explain the role of the op amp in a circuit?
Sure, op amps are incredibly versatile components used in many types of analog circuits. One of their main jobs is to amplify small signals, such as those from sensors, to level the other parts of a circuit can work with. They're also used as buffers where they help prevent signal loss between stages of a circuit by offering high input and low output impedance, basically acting like a strong relay that doesn't load down the signal. Op amps can also serve as comparators, deciding which of two input voltages is higher and switching the output accordingly, useful for detecting thresholds or triggering actions. In signal processing, op amps are used as integrators and differentiators to shape waveforms or perform analog math operations. They're key parts of active filters, which allow only certain frequencies through which are essential in audio, communications, and control systems. When you need to combine signals, op amps can act as summing amplifiers, adding multiple inputs together with precision. For more sensitive tasks like reading signals from medical devices or industrial sensors, op amps are often used in instrumentation amplifier, which amplify very small voltage differences while ignoring noise common to both inputs.
Let's also walk through the parameters we need to consider for op amps. We need to think about supply voltage, right?
The supply voltage is super important when working with op amps because it basically defines how high and how low the op amp's output can go. Think of it like setting the ceiling and the floor for the output signal. If you're using plus or minus 15 volt supplies, for example, your op amp can swing close to plus 15 volts or minus 15 volts at the output, but not quite all the way, unless it's a special rail to rail op amp, which we'll talk about later. Supply voltage matters when you're designing circuits that run on low voltages, like 5 volts or 3.3 volt systems. If your op amp can get close enough to those rails, your signal might get clipped or distorted, especially if you're trying to use the full range. The supply voltage also affects things like how fast the op amp responds, how much gain it can handle at high frequencies, and how much power it uses. So picking the right op amp means making sure it works well with your system supply voltage and that it gives you the performance you need within the range. A mismatch here can cause all kinds of problems, from limited signal swing to the op amp not working at all. On the next slide, you can see how supply voltage and other power supply specifications are written on the datasheet. You can see here the parameter, how it was tested, and its mean and max values. It says here that this particular part works between 6 volts up to 40 volts. 6 volts doesn't mean it only works at this level. It may be plus or minus 3 volts since op amp doesn't care about the value of the positive and negative supplies, and only the voltage between them.
Okay, so Gaz, we also need to consider voltage offset as well, right?
Correct. Input offset voltage is the small DC voltage you need to apply between the op amp's inputs to get 0 volts at the output, even when it should ideally already be 0. In a perfect op amp, if both inputs are equal, the output should be 0. But in the real world, due to mismatches inside the input transistors and other imperfections, the op amp acts like there's a tiny phantom voltage pushing the output one way or the other. That's the offset. This offset is usually in the microvolt to millivolt range, and it becomes very important in precision applications like sensing small voltages from sensors or low gain amplifiers. Left unchecked, it can introduce errors in your signal chain. This is the voltage offset on the datasheet, specified at different temperatures, common mode, and even the package it was tested on.
Okay, so what about input bias and input offset current?
Input bias current is the small amount of current that flows into the input pins of an op amp because the internal transistors need it to operate. It's usually very small, often in the nanoamp or picoamp range. On the other hand, input offset current is the slight difference between the bias currents flowing into each input. Think of an op amp's input terminals like two straws sucking in a tiny bit of drink. One straw is for the inverting input or the minus, and the other for the non-inverting input or the plus. Ideally, both straws should sip the same exact amount. This is the input bias current. But in real life, one straw might be just a bit wider than the other, so it sips a little more. That tiny difference in sipping is called the input offset current. Even though the total current at each input is small, the mismatch between them can cause imbalance in your circuit. Input bias current is small, but if your circuit has resistors at the inputs, the little bit of current can cause tiny voltage drops across those resistors. And because op amps are super sensitive to voltage differences between their inputs, this can throw off your signal and cause the output to be slightly wrong, even if your actual input voltage is correct as seen on this transfer function. It's good practice to match the resistor values at the inputs to reduce its impact. Again, this is what it looks like on the datasheet. You can see it on the input characteristics section and they are specified altogether.
Okay, so we also need to look at bandwidth as well, correct? So walk me through this design consideration.
Sure, bandwidth in an op amp tells you how fast it can respond to changing signals. It's the range of frequencies the op amp can handle without the output getting weak or distorted. If your signal changes slowly, low bandwidth is fine. But if you're dealing with audio, fast pulses, or high speed data, you need enough bandwidth so the op amp can faithfully follow the signal. Imagine trying to sing along to a fast song, but you can only speak slowly. You'd fall behind. That's what happens when a signal moves faster than an op amp's bandwidth. It can't keep up, and output becomes inaccurate. Bandwidth also ties into something called loop gain, which helps the op amp correct errors and keep the output clean. As frequency goes up, loop gain goes down, and if it drops too much, performance suffers. So having enough bandwidth ensures the op amp can respond quickly, stay stable, and deliver a clean, accurate output, especially in high speed or high precision applications. This is the bandwidth of an op amp in a datasheet. When you're designing with op amps, it's tempting to just look at the specified bandwidth value, usually listed as the gain bandwidth or the negative 3 dB bandwidth. But the one number only tells part of the story. To really understand how your op amp performs across the frequencies, it's important to look at the frequency response graph. This graph shows how the op amp's gain drops off as frequency increases, and it gives you a clear picture of how much loop gain you have at different frequencies. That's crucial for predicting stability, phase margin, and accuracy in real world conditions.
Okay, so I think we also need to talk about slew rate. So, what does that look like?
Slew rate is how quickly an op amp can change its output voltage in response to a fast changing input signal. When the signal rises or falls rapidly, you need an op amp that can keep up. The slew rate is too slow, the output can follow fast enough, and the signal becomes distorted or sluggish. Imagine trying to follow a fast moving object with your eyes. If you react slowly, the object blurs or slips out of view. That's exactly what happens in an op amp with a slow slew rate. The output lags behind and misses the sharp edges of the signal. Choosing an op amp with a high enough slew rate keeps your output clean, sharp, and accurate, especially when dealing with fast or large voltage swings. This is your slew rate specified on the datasheet. It is usually in volts per microsecond.
Okay, so Gaz, what about voltage noise?
Noise in an op amp refers to tiny unwanted voltage fluctuations that are always present at the output. This is even when there's no signal. It comes from internal transistor activity and resistor thermal effects. And while it's usually small, it can seriously affect low level or precision signals like those from sensor or microphones. Imagine trying to listen to someone whispering in a crowded room. If there's too much background noise, you miss the message. That's what happens when an op amp's noise is high. It drowns out the weak signals you're trying to amplify. This is why low noise op amps are critical in applications like audio, instrumentation, and data acquisition, where even a few microvolts of noise can blur the accuracy of the signal. This is a sample noise computation under two different conditions, each with a different cutoff frequency. The key idea here is that the wider the bandwidth, the more noise gets through. In other words, noise accumulates over frequency. So if your circuit allows unnecessary high frequency content, you're also letting in more unwanted noise. That's why it's crucial to optimize your bandwidth, only allowing just enough to pass the signal you care about. For example, if your input signal is limited to 1 kHz, designing for a 100 kHz bandwidth just adds extra noise without benefit. By using a low-pass filter or selecting components with an appropriate bandwidth, you can minimize the integrated noise, improving your signal-to-noise ratio and overall performance. This concept is especially important in low-level analog designs, such as sensor readouts, where noise can easily mask your real signal. Just like the bandwidth, the datasheet might list a single noise figure, like voltage noise density in nanovolt per root hertz. This doesn't tell the full story. Look at the noise plots. That usually shows noise versus frequency. These plots reveal how the op amps behave over the full frequency range, including the low frequency, 1 over F noise region, where noise increases sharply. This is crucial if your application deals with low frequency signals because the 1 over F noise could dominate. On the other hand, if your signal is in the audio or megahertz range, you'll be more concerned with the flat band noise region, just like judging a song by hearing the whole track instead of one note. Reviewing the noise plot helps you choose an op amp that performs quietly where it matters most in your circuit.
All right. So, can we also look at input voltage range as well?
Yeah, the input voltage range of an op amp tells you the span of voltages that you're allowed to apply to the input pins while still expecting the op amp to behave properly. If your input signal goes outside this range, the op amp might stop amplifying correctly, distort the signal, or even latch up. Think of it like a doorway. Your signal needs to fit through to be processed properly. If your input is too tall or too wide for the doorway, it won't get through, or if it gets jammed and throws everything off. This is especially important in low voltage systems or when using single supply op amps, where the input range might not go all the way through the positive rail. The input voltage range depends on the supply voltage. It defines how close your signals can get to the supply rails. Sub op amps can handle inputs all the way to the rails.
All right. So, can we also talk about the input output rail to rail a bit as well?
Rail-to-rail input and output means the op amp can handle input signals that go all the way down to the negative supply and up to the positive supply, and also drive the output across the full range. This is really important in low voltage or single supply systems where every bit of voltage range counts. While many op amps are labeled rail-to-rail output, no real-world op amp can perfectly reach both supply rails under all conditions, especially when driving a load. That's because of voltage drops across internal transistors in the output stage. Even in rail-to-rail designs, the output usually comes within a few millivolts to a few hundred millivolts of each rail, depending on load current and supply voltage.
Okay. So, Gaz, before we move on, can you recap these parameters a little bit?
Sure, the supply range tells you what voltage the op amp needs to run. Some work on low single supplies like 3.3 volts, while others need higher dual supplies like plus or minus 15 volts. Voltage offset is a tiny built in error between the inputs that can affect accuracy, especially in precision circuits. Input bias current is a small current that flows into the input pins. It's usually tiny but can matter when working with high impedance sources like sensors. The gain bandwidth tells you how much gain an op amp can provide at higher frequencies. Higher is better for fast or wideband signals. Related to that, slew rate describes how quickly the output can change. If it's too slow, your fast signals will come out rounded or distorted. Every op amp also adds a little bit of noise, which is like a faint hiss on your signal. Lower is better for clean measurements. The input voltage range tells you what input levels the op amp can handle safely without misbehaving. And the output loading refers to how much current the op amp can deliver to your load. Too much load can cause a signal to droop or distort. Using rules of thumb when working with op amps is a great way to get started. They're like shortcuts based on real engineering experience. Quick checks that help you avoid common mistakes and pick something that's probably good enough early in your design. If you're just figuring out what kind of op amp you need or trying to narrow down your choices, these rules can save you a lot of time.
Fantastic. Now, Gauze, it's important to consider what application you're designing for when considering these different traits, right?
Yes, matching an op amp's performance to your application is all about choosing the right tool for the job. Not every op amp is built the same. Some are fast, some are precise, some sip power, and others can drive heavy loads. For example, if you're working with audio, you'll want low noise and low distortion. For sensor signals, low offset and low eye bias current are key. If it's a battery power device, go for low power consumption. High speed data, then you'll need high bandwidth and fast slew rate. It's like picking a car. Are you off-roading, racing, or commuting? Each application has different demands, and picking an op-amp that's designed with those in mind saves you from headaches and give you better performance where it really counts.
Okay, so Gauze, there are different families of op amps, correct?
I'd like to call them families, but they are actually input stage types, topologies, and architectures. Op-amps come in different types, each with its own strengths and trade-offs. Bipolar amplifiers use bipolar junction transistors, offering low noise and high gain, making them great for general purpose and audio applications. But they draw more input bias current. Zero drip amplifiers use clever internal tricks to constantly correct offset errors, giving you extremely low offset and drift over time and temperature. Ideal for precision DC measurements, though they may introduce switching artifacts at higher frequencies. JFET amplifiers use junction field effect transistors and have very high input impedance and low bias current, making them a good fit for things like photodiodes or pH probes, though they may have more offset and noise than bipolar types. CMOS amplifiers are known for ultra low power and very low input bias current, perfect for battery powered and portable devices, but their noise and offset can vary more. Difference amplifier outputs the difference between two input signals. It's often used to remove common mode noise and extract signals riding on noisy background. Current sense amplifiers are designed to measure current by amplifying the voltage across a small sense resistor. A TIA converts input current into output voltage, making it perfect for photodiodes and optical sensors. It's highly sensitive and often used in light detection and precision optical circuits. FDAs handle differential signals from input to output, making them ideal for ADC driving, high speed communications, and precision signal chains. They offer excellent noise immunity and common mode rejection. Instrumentation amplifier is built from multiple op amps to achieve high input impedance, accurate gain, and strong rejection of noise on both inputs, perfect for low level sensors like ECGs or bridge circuits. PGAs let you digitally adjust the gain of your signal using control inputs, often SPI or I2C, which is ideal when you need to adapt to varying signal levels without redesigning the circuit.
Okay, so what kind of system constraints should we keep in mind?
When designing with op amps, there are several system constraints and trade offs to keep in mind to make sure your circuit performs reliably in the real world. There's always a balance between speed, precision, and power. Faster op amp tends to consume more power, and high precision ones can be slower or more expensive. Power consumption is a key factor in portable or always on devices, so low quiescent currents is often a must. You'll also need to match the op amp's supply voltage to your systems. Not all devices work well with low voltage rails, and some can handle signals near the supply edges unless they're truly rail to rail. Be cautious of input offset voltage and bias current. Small errors can become big problems. Check whether the op amp can handle your output loading. Heavy or capacitive loads may need a buffer or compensation to avoid distortion or instability. If you're working with a small signals, noise is another silent killer. A noisy op amp can bury useful information. The circuit topology you choose, like transimpedance, difference, or programmable gain amplifier, should match your application's needs for signal type and accuracy. Cost is also part of the equation. You may not need the most expensive part if your requirements are modest, but cutting corners on performance critical specs can cost more in the long run. On top of that, consider the operating temperature range, especially for automotive, industrial, or outdoor environments. Some op amps are only rated for 0 degrees to 70 degrees Celsius, while others are designed for negative 40 to 125 degrees Celsius or more. Lastly, don't forget the physical package. Tiny packages save board space but may be harder to solder or less thermally efficient, while larger ones are easier to handle but take up more room. All these factors help you choose the right op amp, not just for schematic, but for your whole system.
Okay, so Gauze, before my audience purchases an op amp for their next design, what should they do?
So before they buy an op amp, it's important to walk through a few thoughtful steps to make sure you get the right part for your design. Start by clearly understanding what your circuit needs, and once that clear, list the essential parameters like supply voltage, input or output range, offset, gain, and bandwidth. Then choose an op amp family that fits your general application. There are types tailored for general purpose, precision, high speed, low power, and others. Next, make use of selection tools and parametric search engines provided by manufacturers to help filter your choices. Once you've narrowed it down, shortlist based on key specs that align with your design needs. From there, validate your picks by reading the datasheets carefully. Pay attention not just to the typical values, but also the limits, graphs, and test conditions. Lastly, simulate your circuit using tools like SPICE models and LT-SPICE, and use available resources like application notes and evaluation boards to test performance and ensure a solid design before purchasing in volume. These steps help you avoid surprises and lead to a more robust and cost effective design.
Gauze, given all that we've talked about today, how do we go about choosing the right amplifier for our next design?
Choosing an op amp isn't just about picking one with good specs. It's about finding the one that's the right fit for your application. Because different applications need different things. It's not just about picking the fanciest or fastest one, it's about picking the one that makes the most sense for your circuit. So once you understand the role it plays in your specific application, choosing the right one becomes much easier and your design is more likely to perform the way you need to.
Gauze, can we also walk through some applications as well?
In a high precision laboratory weight scale, the system is designed to measure extremely small weight changes down to a micrograms, with a target error of less than 1 LSB. To support this level of accuracy, the sensor must offer very high resolution, up to 2 million steps or about 21 bits of resolution. This translates to an incredibly fine system sensitivity of 10 nanoampere per LSP, based on a full-scale sensor current of 20 milliampere. To convert this current into a usable voltage, a large shunt resistor is assumed about 400 ohms, which yields 4 microvolt per LSP. At full scale, this setup produces a signal of 8 volts, 20 milliampere multiplied by 400 ohms. Given the tiny voltage, step size, and high resolution required, selecting components like op amps with ultra low noise, low offset, and high linearity is essential to accurately capture and amplify these signals without introducing errors. Based on what we've learned from the previous slides, the ADA4077 stands out as a strong candidate. It's a well-known op-amp with low noise, low offset, and low drift, making it a suitable choice for this application. So, despite the good specs of ADA4077, the total error amounts to 30.3 microvolts, which is equivalent to 7.6 LSB, well above the desired sub-LSB target. The error breakdown shows the main contributor is the voltage offset drift, which adds 30 microvolts alone. Even though the op-amp has a relatively low input offset by 35 microvolts, which is calibrated out so it doesn't factor in, the 1 over F noise contributes a minor 300 nanovolts. To address this, why not use zero drift amplifier? Zero drift amplifiers has a very low offset voltage, an impressively low temperature drift, and a minimal 1 over F noise. Using ADA 4523 lessens the total system error to only zero point 0.9 microvolt or zero point 0.2 LSB. This is now well within the design goal. Additionally, the ADA 4523 supports a wide input voltage range, which is critical since the system needs to handle up to 8 volts input. This is a requirement that ruled out alternatives like ADA 452H with its 5.5 volts limit. This reinforces the importance of carefully matching the op amp specifications to the application and shows how a zero-trim amplifier can significantly improve accuracy in high-resolution analog systems. This example shows how to design a circuit for ultra-low current sensing using a photodiode, which converts light into a tiny current. To turn that current into something we can measure, we use a transimpedance amplifier. In this case, the goal is to get a 5 volts output when the input current reaches 2 nanoampere, which means we need a very large 2.5 gigaohms feedback resistor. Because the signals are so small, the op amp itself needs to be incredibly quiet, specifically. It also needs an input bias current in the femtoampere range. Otherwise, the op amp could inject more current than the signal itself. Luckily, the ADA 4530-1 is a great choice here. It's designed for this kind of work with ultra-low input bias current, just 20 femtoampere, a decent 2 MHz bandwidth, and smart features like an integrated guard buffer to keep the signal clean. This kind of setup is perfect for very sensitive applications like light meters, scientific detectors, or lab instruments where every tiny bit of current counts.
Okay, so Gauze, what about a three-phase motor control design?
So in this example, it shows how we can accurately measure current in a three-phase motor control systems, which is super important for keeping the motor running smoothly and safely. The setup uses tiny shunt resistors to sense current in each motor phase. These resistors are low cost and reliable, making them a great choice for real-time current feedback. But since the motor uses PWM or pulse width modulation to control speed and torque, there's a lot of fast switching happening, so the op amp you use needs to be fast and able to filter out all the switching noises. The current can flow in both directions, so the op amp also need to handle bidirectional signals and a wide range of input voltages. That's where the AD8410A comes in. It has a high bandwidth of 2.2 MHz to keep up with fast signals, very low drift, and strong noise rejection, so you can get clean, accurate readings even in noisy environments. It's a great hit for motor control applications where performance and reliability really matter. In this slide, we're looking at a multiplex data acquisition system, which is common when you're trying to monitor multiple sensors like photodiodes, thermocouples, bridge sensors, and current monitors with a single ADC. The key challenge here is that the multiplexer, or MUX, switches rapidly between channels, and each sensor can sit at very different voltages. That means the op amp acting as a buffer has to handle large differential voltage steps and still settle quickly to maintain the system's sampling rate and accuracy. Now here's where the ADA 4510 really shines. Unlike many op amps that use internal back-to-back diodes, which can introduce charge injection or input loading, the ADA 4510 is designed to tolerate large input differentials all the way to the rails without clamping or distortion. It also has high bandwidth and fast settling, which are critical in this fast switching environment. Plus, its low inrush current helps reduce voltage glitches and signal disturbance after each switch, making it ideal for clean transitions in systems like this. So if you're building a MUX-driven signal chain and need an op-amp that's fast, clean, and robust, the EDA 4510 is an excellent choice. It's built with exactly these challenges in mind.
Fantastic. Okay, so Gauze, what kind of resources does Analog Devices offer to help me here?
So Analog Devices has the ADA Precision Studio, which is a very helpful web-based tool from Analog Devices, designed to make precision analog design a whole lot easier. It gives you access to a range of calculators and design tools tailored for things like op amps and signal chain design. The platform helps you pick the right components, calculate performance parameters like gain, noise, and bandwidth, and even simulate behavior using LT-SPICE models. What's really nice is that it pulls in real product specs from ADI's catalog, so you can build and test circuits based on actual devices, not just ideal models. It's a great way to explore different design options before jumping into hardware. Plus, it's all online, so no installation, hassle, just log in and start designing.
Excellent. Well, Goz, I think that's all I have time for today. Thank you so much for joining me.
Thank you.
And before we go, you didn't forget to click that link, did you? There you can find even more information about this topic from Analog Devices. For Chalk Talks, I'm Amelia Dalton from eejournal.com. For more Chalk Talks, head on over to the Chalk Talk section of EE Journal. You can't miss it, it's right across the top. Or head on over to YouTube, youtube.com/EEJournal.